Hi everyone, this is going to be your video for part one of the chemistry fundamentals notes. So to get started, I just want to say that most of you probably heard this lecture in class, but this is meant to be a resource for you if you missed it in class or if you wanted to go back and rehear an explanation of any particular topic. So to start out, we're going to talk about matter. Matter being anything that has mass and occupies a particular volume. So we have the three main states of matter being solid, liquid, and gas. Solid matter is going to have strong intermolecular attractions between whatever molecule or atom happens to be present in that solid. They have low kinetic energy because solid atoms, solid molecules, anything like that, they're not going to be moving around, and kinetic energy is the energy of movement. Solids also have a fixed volume and shape, and that makes sense if you think about it, because if you take a solid object from one container and put it into another container, it's not going to change size or shape. It has fixed size and shape. Liquid has a fixed volume, however, it's going to take the shape of its container. So with a liquid, a little bit weaker intermolecular attractions between the molecules there. And you can kind of see that in this drawing down here, because we can see that the molecules are right up next to one another, but they can slide around each other. So that accounts for the liquid property of taking the shape of its container. Gases have no set volume or shape, and they take the shape and volume of the container that they are put in. And that makes sense if you think about it, because if you see all of this space around the gas molecules, you can compress gas molecules closer together. Whereas over here, you can't squish the solid molecules any closer than they already are. And the liquid molecules are pretty much right up on each other as well. So that compression can't take place like it can with a gas. Plasma is the fourth state of matter. Unfortunately, we're not going to spend a lot of time on it in this class, but basically, as energy increases, electrons are going to come away from the atoms that they are associated with. And what that creates is a sort of ionized gas, and that's what plasma really is. So as atoms start to lose their electrons and become ionized, and the electrons are kind of free floating and the nuclei are free floating, that's where you get plasma. Moving on to types of substances, we have matter being divided into two categories, a pure substance and a mixture. A pure substance has a fixed composition and fixed properties, whereas a mixture is two or more pure substances mixed together, and those properties will change. So a pure substance could be either an element or a compound. So you can have iron would be a good example of a pure substance, but salt, sodium chloride, would also be an example of a pure substance. Iron is one element, and salt, sodium chloride, is a compound. But compounds, even though they contain more than one thing, have unique properties of that particular compound. So if we were to rip apart sodium and chloride apart would have very different properties than sodium chloride together. On the other hand, we have a mixture, and mixtures can either be homogeneous or heterogeneous. And if you look at the drawing, or I guess graphic, I should say, a homogeneous mixture is really a mixture of substances, but they're all interspersed together, versus a heterogeneous mixture, two substances that are mixed together, but one substance tends to congregate with itself and the other substance tends to congregate with itself. And then down here, the last part of this slide is a definition of a molecule versus a compound. So you've heard this before in regular chemistry, but I will reiterate it again. Molecules are two or more atoms that are covalently bonded together, and a compound is going to consist of two or more different elements that are either bonded covalently or ionically. So there's a couple of differences there, but what I'd really like to focus on is that a molecule doesn't necessarily have to have two or more different elements in it. For example, oxygen gas, O2, is a molecule, but it is not a compound, okay? Versus something like CH4, methane, that is a compound because it has carbon and hydrogen in it, 2 or more different elements, okay? And then the last thing that I would like to say or make a note of, and I said this in class, but alloys of metal, spelled alloy, those are going to be considered mixtures. They are not considered compounds, so they are not pure substances. So alloys are going to be mixtures once again. Next, we're going to touch on energy really briefly. We will dive very far into depth on energy in this class, but that's not going to be for a couple of units. So for now, what I want you to know about energy is that it is the ability to do work. Absolute zero is defined as the point where all atoms stop moving, and that's going to happen at negative 273 degrees Celsius or 0 degrees Kelvin. Absolute zero is 0 degrees Kelvin, but in Celsius, that's negative 273. In terms of energy, we have kinetic energy, which is the energy of motion. So kinetic referring to motion, and then potential energy being stored energy due to something's position. So if we look at the graphic over here on the right, this ball on the left-hand side of the graphic has potential energy because it's not currently moving, but it's being held over the edge of a precipice. So it has the potential to have energy, right? Versus when that ball is released and it starts moving downward, that ball is going to have kinetic energy because it is currently moving. Next, let's talk about the first law of thermodynamics. It is very similar to the law of conservation of mass in that the law of conservation of mass states that matter can neither be created nor destroyed. And so energy, much like mass, can neither be created nor destroyed, only moved around. So in any particular reaction or any particular thing that happens, the energy of the before state will match the energy of the after state, but that energy may have moved around a little bit. So to give you an example in terms of reactions, reactions can either absorb or release energy to or from their surroundings. But the total energy of the system in general hasn't changed. It's just moved from somewhere to another place. But again, the energy total before and the energy total after is the same. Significant figures have to do with accuracy versus precision. So the last value in any measurement that we could possibly take in this room or any scientist could ever take ends up being a guess. So if you think about that guess, if I am stepping on a scale at my house and it's going to measure my weight down to the 10th place, that 10th place is kind of a guess in a way because the scale can only be accurate to so far. So it's going to measure as far as it can, but anything past that is unknown, right? So let's say, for example, that somebody steps on a scale and their weight is 150.0 pounds, according to that scale, right? But you don't know what's after that. The scale may not measure what's after that. So that next number could be a 7. Or it could be a 3, or it could be anything. And so because that scale doesn't know an infinite amount of decimal places, this is a best guess. Because if it was a 7, then that would round up to 150.1. If it was a 2, it would round down back to 150.0, right? So again, any measurement is a guess. And that's why significant figures are important. So let's say you're doing a calculation with 10 grams, but also, I don't know, a speed of 157.365 meters per second. Let's say you had to do a calculation with 2 of those numbers. One of those numbers is far more specific than the other. But if you include both the very unspecific number and the very specific number, your answer is going to be pretty unspecific because of this number. So that's why when we do calculations, we round our answer to the least number of significant figures, because that is as far as we can be sure of using numbers of different significance. Okay, so all of these are going to be your rules for significant figures, but quite frankly, I like to think of it logically versus using all of those rules. So our next slide is a little quiz. How many significant figures do each of these numbers have? Well, we know that any zero that's in between non-zeros is going to be significant. So if we count 1, 2, 3, 4, 5, this number is going to have 5 sig figs. We know that leading zeros are insignificant. So these 3 numbers are significant, meaning that there's 3 sig figs in that particular number. We know that lagging zeros are insignificant, which means there's only 1 sig fig in this number. But we know that zeros that take place after a decimal place are significant. So we need to count 1, 2, 3, 4, 5, 6, 7, 8 sig figs in this number. And if you're struggling with why these zeros matter, but these zeros do not, think of it like this. If you could get rid of those zeros with scientific notation, they are not significant. But if you would have to write those zeros in scientific notation, then they are significant. Another way you can think of it is, why would I write all of those zeros following a decimal place unless I was absolutely sure of that number to that many decimal places? So those are a couple of things that I think about when I am doing sig figs. All right, rules for rounding off. This is more about math with significant figures. So in general chem, I kind of teach it all in the same rule, and that is always err to the least amount of sig figs. But there is actually a difference between addition and subtraction with significant figures and multiplication and division. So with addition and subtraction, you're going to want to pay attention to how many decimal places exist and round your answer to the lesser one. So 14.36 has 2 decimal places after it. 2.149 has 3 decimal places after it. So once we do that addition, we're going to round off our answer to 2 decimal places. Versus with multiplication and division, we count all the sig figs in both numbers. 14.36 has 4 significant figures. 2.149 also is going to have 4 significant figures. And I do apologize, but this is meant to be a multiplication symbol here. So if we were to multiply these 2 together, we would get some sort of answer, which we would then round to 4 significant figures. Actually, you know what? I think I lied to you. That's supposed to be division. My apologies. But either way, regardless of what the math actually is, multiplication or division, the steps are the same. You're going to round to 4 significant figures if 4 significant figures exist in both of your numbers. Metric system standard units. So standard units are important to know because a lot of problems will require numbers to be in those standards units to use those formulas. So a lot of times mass needs to either be in kilograms or in grams. Length is a lot of times going to need to be in meters. Volume is going to need to be in liters. Sometimes milliliters is okay, but liters is the standard. Current is going to be in amperes or amps for short. Temperature is generally going to need to be in Kelvin. Charge is represented in coulombs. Pressure, the standard unit is pascals. However, you may also see a lot of pressure units. So under other units, you might see atmospheres is one, millimeters of mercury is another. You might see kilopascals as well, or torr is another pressure unit, maybe PSI. But those units, you're going to need to be able to convert between them. Amount of matter you're going to see in moles, and energy you're going to see in joules. The only other unit that I can think of that you're going to see a lot off the top of my head is probably Celsius, represented by a little degree symbol in Celsius. But again, for a lot of formulas, that temperature is going to need to be in Kelvin. Prefixes for converting between metric units are super important to be familiar with as well. So this chart gives you from giga all the way down to pico. More exist. I can tell you that right now. In the homework that's associated with this lecture, you're going to need prefixes that are not in this table, but you can look those up. So this is a similar table to the one that I gave you in Gen Chem, but it's a little bit more compacted. But the real use of this table is to take these numbers here and figure out your conversion factors with them. That's really why it's super important to be able to use this table accurately. So let's look then at some conversions. If I want to cancel unwanted units, I need to use conversion factors to do it. So here's an example of a conversion factor. 1 mile equals 5,280 feet. No, this is not a metric conversion, but we're all familiar with feet and miles. So you could either write your conversion factor 5,280 feet over 1 mile, or you could write it 1 mile over 5,280 feet. Either way, and it's going to depend on what you're converting out of or what you're converting to, which one you choose. So with sample problem 1, how many millimeters are equal to 1.85 times 10 to the 4th picometers? We would set up a basic conversion chart, right? So in Gen Chem, we set up our conversion charts just like this. In this class, you're going to see a lot of this going on, but honestly, it's the same either way. You just imagine that X right there. So our given number usually is going to go in the upper left. In fact, always goes in the upper left. So our 1.85 times 10 to the 4th picometers is going to go there. We have our placeholder 1 down below. And then as I taught you in Gen Chem, the unit that you're converting to is going to go in the top right. In this case, it's millimeters. And the unit that you are converting out of, or the unit that you started with, goes on the bottom right. And that's picometers. And we do that so that picometers can cancel out picometers when we do that multiplication later. So the next step is actually to go backwards a little bit. So bear with me, because we're going to look at that table again to figure out our conversion factor. So if we look at this table, pico is 10 to the negative 12 and milli is 10 to the negative 3. So let's keep that in mind. Pico is 10 to the negative 12 and milli is 10 to the negative 3. So the first thing that we want to do is we want to find the difference between those exponents. So if we took negative 3 minus negative 12, we would get a difference of 9. And that's important because what that tells us is that in every one of our larger unit, which is millimeters, millimeters are larger than picometers, there are 1 times 10 to the negative, or sorry, to the positive 9 picometers in every 1 millimeter, which if you think about it, makes sense because picometers are tiny, right? And millimeters are still small, but they are much bigger than picometers. So there better be a lot of picometers in every 1 millimeter because the opposite would not make sense. Okay, so to solve that problem, what we're going to do is we're going to multiply straight across on the top. We get 1.85 times 10 to the 4th on the top, and we get 1 times 10 to the 9th on the bottom. Our units cancel out, picometers with picometers. So when we do that division, we would get our answer in millimeters. So if we recall how to do multiplication and division in scientific notation, what we're going to do is we are going to separate those numbers into 2 portions. We have our raw numbers and our exponents. 1.85 divided by 1 is very simple. It's 1.85. And then with our exponents, when we're dividing, we're going to subtract them. So 4 minus 9 ends up being negative 5. So we tack in times 10 to the negative 5 on there, and then that is going to be our answer. So hopefully it wasn't super confusing to you how I did that. But if it is, please ask me and I'm happy to clear it up for you. Our next sample problem prompts us to find the volume of 62.3 grams of a gas with a density of 1.2 grams per liter. So there's a couple of ways you could do this. You could either use the density formula, which is D equals M over V, density equals mass over volume, or you could do a simple conversion. So the simple conversion is going to be very similar to what we did up here. And then using the density formula would just be a plug and chug formula. So I'm going to do it that way because I really like using plug and chug formulas. Our density, which we're going to plug in for D, is 1.2. And we know our mass, 62.3. And volume is going to be our variable that we're solving for. So to rearrange that formula, we're going to multiply both sides by V, giving us 1.2 V equals 62.3. We would divide both sides by 1.2, and we would get our answer. Okay. Sorry, my little controls aren't allowing me to write 1.2 under there. But the only thing that you may forget to do now and again with a simple plug and chug is rounding to the correct number of significant figures, because that is important when you do math in this class. So just always remember to look at the numbers that you're given initially and always round your answer to that amount of sig figs. In this case, 2 sig figs, because 1.2 is our least amount of sig figs. So moving on, we have the law of conservation of mass, which states basically a very similar thing to conservation of energy. Matter is neither created nor destroyed. Whoops, too far. So the total mass of substances don't change during a chemical reaction. Your mass before equals your mass after, no matter if it moved around, rearranged itself. Okay. Mass fraction is very, very similar to percent composition. It's just that you don't convert the answer at the end to a percent. So looking at this, we are going to do some math. The question asks you to calculate the mass fraction or mass ratio of nitrogen in this compound right here. So this compound right here is ammonium nitrate, NH4NO3. So we know by looking at that formula, there's 4 hydrogens, there are 2 nitrogens, and there are 3 oxygens in there. So the first thing we have to do is figure out how much the total compound weighs. So if we do that real quick, we're going to do 4 times 1.008. We're going to do 2 times 14.01, and we're going to do 3 times 16. So if you want to do this along with me, go ahead and pause it before I start handing out answers. So doing all the math real quick, we do 4 times 1.008, we get 4.032 for our hydrogen. We get 28.02 for our nitrogen, and we get 48 for our oxygen. So that total molecular weight of the compound is going to be 80.052. And once again, all this information is going to come from the periodic table. So once you have all of that, all that you have to do is divide the weight of nitrogen in that compound, which is this number right here, by your total weight, and then you get that decimal right there. If I were asking for a mass percent, you would then convert that to a decimal and convert that to a percent and tell me, hey, 35% of that entire molecule's weight is nitrogen. But if it's just mass fraction or mass ratio, these numbers here are fine. And also, no matter how much of that particular sample of ammonium nitrate you have, nitrogen is always going to be 35% by weight of that entire molecule, which is very helpful when you're doing calculations later on down the road. Next is going to be the law of definite composition, which states that no matter what the source, a particular chemical compound is composed of the same elements in the same parts or fractions by mass. So no matter if you get water from the river or from rainwater or from tap water, the formula is the same, H2O, 2 hydrogens for 1 oxygen. There may be different impurities in those samples. So there may be ions or something else floating around in there, but the water part of that sample is going to be the same no matter where it comes from. So now we have something called the law of multiple proportions, which states that if elements A and B react to form two compounds, the different masses of B that combine with a fixed mass of A can be expressed as a ratio of small whole numbers. So that's a lot, that's a mouthful. But basically it allows you to take percent compositions and figure out what the formulas are. So we have two oxides here. Oxide number 1 contains 46.68% nitrogen and 53.32% oxygen. Oxide number 2 contains 30.45% nitrogen and 69.55% oxygen. And both of these compounds are going to be made only of nitrogen and oxygen. So looking at this just logically for a second, we could probably intuit that, okay, nitrogen and oxygen weigh almost the same if we look at the periodic table. So if something's almost a 50-50 ratio of nitrogen to oxygen with a little bit of wiggle room for weight differential, the formula is probably this. And looking at the second percent composition, we have about a 30% nitrogen and a 70% oxygen. So that's a little bit more than double oxygen for nitrogen. And again, there's a little bit of wiggle room there for weight differential between nitrogen and oxygen. So you could probably figure that this is the secondary formula. And you'd be right. However, the problem with just doing it this way is that you don't always have two elements that weigh almost the same thing. Some elements weigh a ridiculous difference from the other elements that might be in a compound. So you can't always just logic it out like that. Okay. So let's look at this here. And this is completed for you, so you don't really have to write anything down except potentially, I don't think these lines really came out on your notes, so you may want to fill those in real quick. But to do this mathematically, you could assume, hey, I have 100 grams of each compound. So I can use my theoretical 100 grams of each compound to do a little bit of math and get everything into a ratio form. So if we take oxide 1 and use those percentages from up here and just think about them in terms of grams, if I have 100 grams of a compound that's 46.68% nitrogen, well, I'm going to have 46.68 grams of nitrogen, right? And if it's 53.32% oxygen, I'm going to have 53.32 grams of oxygen. So my first step is going to be to divide both of those gram amounts by nitrogen. Okay, so we've done this 46.68 divided by 46.68, and we've done 53.32 divided by 46.68. This is going to reduce to 1. So this is going to be a 1, right? This one, however, is going to equal a little bit more than 1, 1.142. For our second oxide, we're going to deal with the second oxide's percentages, and we're going to convert them into grams, which again, since we're assuming we have 100 grams of each, is pretty easy. So we're going to divide nitrogen by nitrogen, and we're going to divide oxygen by nitrogen. Once again, this is going to reduce down to 1, and then this one is going to give us another number, in this case, 2.284. So what we're seeing here is something that can be turned into a ratio. Both nitrogens are the same, right? So in each compound, we know that there's going to be one nitrogen, okay? But with the oxygens, it's going to be a little bit different because our numbers for oxygen are different. You are going to take the bigger one, in this case, this number, and you're going to put it on top, and you're going to take the smaller one, that number, and put it on bottom, and you are going to reduce it down to a whole number ratio. In this case, 2 to 1. Both of those numbers cleanly round down to 2 and 1 respectively. So what that tells you is that oxide number 2 has 2 oxygens per nitrogen, and that oxide number 1 has 1 oxygen per nitrogen. And again, we could have figured that out logically because oxygen and nitrogen are so similar in terms of molecular weight, but that's not always the case. So we'll do a warm-up question that's going to be similar to this to kind of clear this up further. Moving on, I'm going to briefly touch on atomic theory. You're not going to be directly tested on this, but it's good to be familiar with the different atomic theories and how they evolved over time. So Dalton's atomic theory states that all matter consists of atoms. Atoms of one element cannot be converted into atoms of another element. Atoms of an element are identical in mass and other properties and are different from atoms of another element. The spacing of that kind of got weird. I apologize. Compounds result from the chemical combination of a specific ratio of atoms of different elements. Okay. And then today, we know that the atom is the smallest body that retains the identity of an element. Elements can only be converted into other elements in a nuclear reaction, i.e. nuclear decay. We'll get there, we'll talk about that. And that isotopes of an element differ in the number of neutrons and thus in mass number. So Dalton's atomic theory was pretty accurate, but there's a couple of things that we know now that he did not know back then. There's a few different atom models over the years that have been the top of the scientific community. We have the Thomson-Reisenbund model. So he proposed that atoms are somewhat like a raisin bun and the electrons are kind of sprinkled all throughout. They would be the raisins in the Reisenbund model. And then we have Rutherford, which is the nuclear model from the Goldfoil experiment, if you've heard of that. And so Rutherford's atom model is on the left here. That's honestly one of the most famous ones that you see a lot. It's a little bit different than the quantum model, which is the more accurate one, but you've all seen this diagram before. And then we have Bohr's, which came slightly before that, which looks a little bit flatter, but you've probably also seen that in a textbook as well. And then Millikan did an oil drop experiment that determined the charge and mass ratio of electrons to the other portions of atoms. Again, I'm not going to talk about these super in depth. If you're curious about them, you're free to look them up on your own. Isotopic symbols is something that we have to go over because you're going to see them quite a bit. So let's take hydrogen, for example. Hydrogen symbol is an H. That would be the X here. That's the symbol. On top, we're going to have the mass number or atomic mass of any particular isotope. And on the bottom, we're going to have the atomic number. So if we recall, all hydrogen atoms have one proton. So their atomic number on the bottom is always going to be a 1. But hydrogen has a couple of isotopes. Hydrogen could either have no neutrons whatsoever and have also a mass number of 1. Or we could have a hydrogen with a mass number of 2, which has 1 proton and 1 neutron in its nucleus. Or we could have hydrogen with a mass number of 3, 2 neutrons, 1 proton. So if you ever see something like this, that's what it means. We're telling you on top the mass number, and on bottom, we're telling you the atomic number. You might also see it represented slightly differently. You might see this going on in some questions, in which case that's just going to be the mass number, citing the nuclear weight of that particular atom. You might see it represented slightly differently. You might see it as an exponent or a subscript or something like that. But most of the time with isotopic symbols, we're talking about the weight. Because as you'll notice, the atomic number, the number of protons, doesn't change. Okay? So average atomic mass. If you took chemistry with me a couple of years ago, we did go over how to do this. If you took it with me last year, we skipped it because of the nature of the COVID year. But it's not all that difficult to understand. All it is if you're finding the average atomic mass of something, which is the number that you see as the mass number on the periodic table, you have to factor in not only the weights of the different, or the masses of the different isotopes, but also their percent abundance, because certain isotopes are much more common than others. So let's take, for example, hydrogen again. We are going to have H1, we're going to have H2, and we're going to have H3. Let's say that hydrogen 1, H1, represents, I don't know, 99% of all hydrogen atoms in the known universe. And then this one is going to represent 0.5% of all of the known atoms of hydrogen. And then this one is going to represent the other 0.5%. The first thing to realize is that all of your isotopes percent abundances have to add up to 100. That's thing one. Thing two is to realize that you have to write these in the formula as a decimal. So if I was going to use this information to figure out the average atomic mass of hydrogen, I would take my isotope 1 mass, so that's H1, and I'm going to multiply that by 99% written as a decimal. I'm going to add that to my second one, my H2, times 0.5% written as a decimal. So we have to write that as a decimal. And we're going to add that to 3 times 0.5%, again, written as a decimal. And once we do that math and add it together, we can figure out the average atomic mass of hydrogen. So if we do that math real quick, we get an average atomic mass of 1.015, which is not exactly what it says on the periodic table because I didn't use the real exact percentages, but we're pretty close to what the average atomic mass of hydrogen is on the periodic table. So again, that's how you're going to use that formula. Isotope mass times its percent abundance as a decimal, followed by isotope mass times its percent abundance as a decimal, etc. Our sample problem 3 is about figuring out the percent abundance if you have access to the average atomic mass and the isotopic weights. So this problem is a little bit more complicated. It asks you, what is the percent abundance of 2 isotopes of boron if the mass of isotope 1 is 10.013 and the isotope 2 mass is 11.009 atomic mass units? So once again, we're going to have to use that formula. But this time we're solving for percent abundance rather than average atomic mass. So we have to look at the periodic table really quickly to figure out what the average atomic mass of boron even is. And checking real quick, I see that boron's atomic mass is 10.81. So using that formula, referencing the formula from before, we know that all of that other information has to equal 10.81 at the end. And we know that one of the isotopes weighs 10.013, and we know that the other weighs 11.009. Okay, so we need to then multiply those by their percent abundances, which we don't know. But what we do know is that if there's only 2 isotopes of boron, those percent abundances have to add up to 100%. And if we were to write 100% as a decimal, that is the number 1, which is good for us because that means that we can represent 1% abundance with X, and we can represent the other with 1 minus X. And now we have a formula that we can solve for X. Okay, so how are we going to do that? Well, we got to multiply some things out and we got to combine like terms. So simplifying this one on the left, we have 10.013x and we have 11.009 minus 11.009x equals 10.81. Now we can go ahead and combine like terms by combining these x terms here. And if we do that, we're going to end up with 11.009 minus 0.996 times x equals 10.81. Then we need to do our 10.81 minus 11.009. And we're going to get negative 0.996x equals negative 0.199. We divide both sides by negative 0.996, and we're going to solve for x. And we get x equals 0.996 1,99799, et cetera, et cetera. I'm going to put a dot, dot, dot after that. Okay, so now we have to do some rounding for sig figs. So I'm going to do that kind of over here. X being the percent abundance for this as a decimal. And we have how many sig figs in our question? We have 1, 2, 3, 4, 5. So we should be rounding this to 5 sig figs. So our percent abundance for our 10.013 isotope ends up being 19.980. And then that's for this one. And then all we have to do is we have to take 100 minus 19.980, and that will give us our other percent abundance. So that's how you're going to do a problem like this. Setting up mathematical equations like that is going to be something that you'll get comfortable with as this class goes on. Just keep in mind that setting up mathematical equations is not different just because we're not in math class. The same relationships that you're seeing in some of your math problems are going to exist here. It's just that we're dealing with chemicals instead of theoretical math numbers. Okay. So at that point, we are at the end of part 1. So I will film part 2 at a later time.